Hello YouTube, De-bodgery here. Welcome to EV Components Review. So this is the power stage for the Fire Driver 96850 controller that I've taken apart. It is bricked right now. The CPU's got a bad flash in it supposedly, and so I'll have to fix that little problem. One of the things I wanted to show you, let me see if I can't get the camera to focus on there. There we go. Yeah, look at all that arcing on there. You should never get that. That's from basically not pre-charging the controller, just taking your battery terminals and just dropping them right onto the studs, and you get arcing just like that. Let's go over to the other one. So this is battery plus over there. Yeah, look at all that scorching on there. That's from not using pre-charge. That's bad. You should never have this kind of thing happen. If you gently bring up the controller, up to voltage, through a resistor, whether you're using a QS8 or QS10 or XT90S connector, you'll never have this happen because you gently bring up the capacitors to charge, in which case you don't fry other things too, possibly. I have killed controllers by not using pre-charge. Only done that once, and that was gracious plenty for me. So, yeah, you should not have all that scorching on your terminals. That is from not using pre-charge and all that inrush current. So you'll notice all these ceramic caps, and in here, that's this is battery plus here, this is battery minus in here, and all those ceramic caps are across there. So there is 18 of those. So Fire Driver, the next time that you do design work for Capacitor, your own company effectively, tell them that you're going to put 18 ceramic caps on every single one of their power stages, like you have done here on the 96850, because this is good, Fire Driver bad. Fire Driver, the last video I saw from Christopher Kleinschmidt, he was showing power stages with 3 ceramic caps, 3 of these exact same ones, not 5 anymore, and that's already inadequate. And yeah, you really need more like, say, 18 on there. So, Fire Driver, it says the same guys, folks, in case you're wondering. Yeah, put more ceramic caps on the Capacitor products. They need them. Okay, so I was showing you those witness marks from the stud that was for that one specifically. And yeah, you can see that same ring right there. Anyway, it's not really compressing. It's not like it's, the board is smashed in underneath. It's just tight enough to make a fit, and that's all. And so it just leaves that little surface mark on the solder trace or the solder pad rather than compressing it like you see in the Capacitor's, because they just over crank those screws. All right, so there is some MOSFET. So magnet chip MDE S14 N045s. These are 135 volt MOSFET rather, from Magnet Chip, which is one of my favorite brands. They're every bit as good as like Infineon or IXYS or onsemi or AOT. They're all good brands. I would use them all interchangeably if they had a component that served my purposes. Anyway, so this guy's rated for 135 volts. 180 amps. The internal resistance is a little bit high, but it's not really all that surprising for 135 volt MOSFET. It's 4.5 milliohms, so pretty decent package. So I'm going to take a little segue here about MOSFET packages and drop this in here and drop this in here. All right, so we have 3 different MOSFET packages that are extremely similar. So this is TO220. In fact, that MOSFET came out of whatever that was, an ASI controller. I don't remember if that was a BAC 8000 or a BAC 4000, but yeah, that came out of one of those. And this came out of a Suron controller. Anyway, the TO220 package was this one, and this is TO163. The only real distinguishing factor between the two is the lack of tab, or you have a tab, and then of course how you apply them. So with the TO220 package, in these 3 legs, you're supposed to put them through holes in a circuit board and then solder them in place and then secure them to a heat sink through the tab. Whereas the TO163 package, you just lay it down flat, like say on a metal core printed circuit board like this, and solder the legs and the tab down, and you're done. So all the cooling is still done the same all through the tab on the back. The leg limits are exactly the same. So fat part is 75 amps, skinny part is 25 or 50 amps, 75 amps, 50 amps. TO220 and TO163 package specs are identical. And in fact, if you put the exact same MOSFET die in either one of these two packages, they would actually perform pretty close to identical because there's really no difference between the two, just how you mount them. All right, so this is the TO263 7P. 1, 2, 3, 4, 5, 6, 7 legs, hence the 7P or 7 pins. There's a bunch of manufacturers that use this package. The reason why I'm showing you these three MOSFETs is I've talked many times about MOSFET leg limits. And so, yeah, that comes up right now. So TO163, TO220 have the exact same leg limits. Basically, 75 amps DC for the fat part and 50 amps for the skinny part. Well, if you notice here, this is the gate leg, and then you got 1, 2, 3, 4, 5 legs in parallel, and those are the source legs, and they are the same width and thickness as the skinny parts on these guys. So 50 amps for each one of those times 5, that's 250 amps DC. So much more current carrying capability out of the package than what you have in TO220 or 163. Yeah, more optimized for current capability. So you can have the exact same die inside here or here and here, and this one is going to outperform these two just because it's not limited by its legs. You could have the exact same MOSFET die inside here, and this would outperform these just because it's not limited by its legs. All right, that's about all I really wanted to say about that. There is reasons why different MOSFET packages are used, like the TOLL package, again, more optimized for current carrying and capability, but physically about the same size as this is, really not a whole lot different, but much more optimized than this is for current, because it actually has one more leg that goes down, that gets soldered down for the source, and still the whole back of the package is your drain. So yeah, more optimized for current than even this is, because that little pin right there is actually electrically the same as the tab on the back, and it's just wasted. Why not make that another source pin like these 5 are, and that's going to give you even a little bit better current carrying capability. So better package for sure than TO220 or 163 like that is. So this is what's used in the 96530, and that package is part of the reason why it's a lower amperage controller. All right, let's see. So the phase buses on here, 2 of the 3 are kind of weird, and the third one is something that is pretty darn good. So this is battery plus, this is battery minus, all in here, and I'll talk about that some more later. But anyway, you'll notice we got 3 MOSFETs here and 3 more here, and that's all the 6 high side MOSFETs for this phase, whatever that's called. I think that's U on the controller. And yeah, they come around this corner right here, and then right here this is all battery minus, and these ones make this kind of L shape too, and those are your 6 low side MOSFETs. Well, in between, across those tabs, through this little piece of copper for whatever reason, across these legs right here, across in here, and across those tabs, that's all your phase bus. Why they didn't just lay all this stuff out in 2 nice neat rows, I don't even begin to have a guess for why they didn't, but yeah, they didn't. Anyway, that's super cool. Not a very good design to do it this way, but there it is. And why they even bothered with this little snap, little piece of copper, I don't even know about that one either. Yeah. This is very much reminiscent of what you see in KMOTO controllers. You just like little random bits of copper that don't really do much good. Yeah, I don't know why they did that. The middle phase, that's this one right here. This one is actually pretty darn good. So, you know, here's your low side MOSFETs. This is battery minus across here. This is your low side MOSFETs. Nice even row, closely placed together. Here's your high side MOSFETs. Nice even row. Here's your battery plus bus. nicely placed together. Here's your phase bus. It's not reinforced. I would like to see that. And they could have changed this a little bit to make this better and not have to reinforce it. Just bring these MOSFETs right up to here. Like ASI and Trampa, they don't use reinforcing at all in their controllers, and they do just fine. But the reason why they can get away with that with just circuit traces is their current paths are also very, very, very short. Or if it is far away, then they're very, very, very big. Big pieces of sheet copper to be able to pull that off. So like in the case of this, if this was not adhered down to a metal core printed circuit board like it is, I bet at 850 phase amps or even 600 phase amps, probably this little copper foil right here is going to get pretty darn warm. But it's able to sink its heat away to this aluminum very quickly because it's literally mounted right to it. So it probably doesn't get very hot. But yeah, this should be reinforced or made tighter. I would definitely rather see it be reinforced. All right, so right down here, that little guy right there, that's the one thermistor, one temperature sensor that's on this power stage. And it's right in the middle of the best of the three phases. So it's a pretty central place to put it. Not too bad. Would like to see one per phase, but this is going to get you most of your temperature readings. This phase is just like the other one, just mirror image. Nothing real special about it. Something I've never mentioned before, knew about them, I've never really bothered to talk about it, but I will now, is Snubber circuits. So this little capacitor, this little resistor. So here's your phase bus, here's battery plus, and you have high side and low side Snubber circuits. If you want to go Google about those things, feel free. But it basically comes down to a cap and a resistor that are going to deal with certain kinds of issues in controllers. Right here, so here is your phase bus across the back side of there, and you get this little trace, another capacitor, another resistor, and this is battery minus. So there's the low side Snubber circuit for this phase. Here is the center phase right here, and here is your high side Snubber circuit. So there's your phase bus, capacitor, resistor, and you can have these backwards. You could have resistor, capacitor, resistor. It really wouldn't make any difference because they're in series. But anyway, phase bus, battery plus, there's your high side Snubber circuit, phase bus, resistor, capacitor. There is your low side Snubber circuit. So I was glad to see those in there. Haven't really commented on that in the past, but super cool to see it there. I've seen other controllers that don't have them. Like I'm trying to remember, I don't think I've ever seen it like in a Trampa controller Snubber circuit. I think I've seen them in like ASIs. Others, like say, let's see, pretty sure I've seen them in like Nuclears, ASIs, a lot of Utronic stuff's got them. I don't think like Flip Sky does. Just kind of depends, if you're going to like start eliminating things, yeah, you do things like this, take those out. So yeah, I was kind of pleased to see Snubber circuits in this FAR driver. So good job, FAR driver, on that. Those are super useful. Yeah, there's another one right there. But yeah, lots of ceramic caps, super cool. Please do this when you make FAR driver stuff, KO Moto stuff. Yeah, I keep doing that on purpose, folks, in case you're wondering. Because FAR driver and KO Moto are one and the same. Yep. Okay, folks, I think that's everything I want to show you on this controller. This is probably my favorite power stage I have seen yet from FAR driver by a lot. Still not perfect. It's just better than everything else I've seen. So anyway, take care, folks. Talk to you later. Bye.